Hey everyone, my name is David Hull, and today I'll be discussing my findings from the Physics 2211 lab for oscillations. So I'll start with a quick introduction. The purpose of this lab was to use the data from a given video of a mass in oscillation to plot the energy changes in the system. We then computed this using a computational model in GlowScript and determined if the model followed the energy principle. And then the system's total energy remained at 0. Some important equations we will need for this lab include Newton's second law, the energy principles, and force equations. We know Newton's second law can be written as the net force equals to the change in momentum over the change of time, as discussed in past labs. And then it's also important to know that the net force in this lab is the force of gravity plus the spring force. Lastly, we need to know that the total change in energy is equal to the change in kinetic energy plus the change in potential, gravitational, and spring energies. In this lab, the system is the mass, spring, and Earth, and there are no surroundings. Since the change in energy of the system is equal to the work done by the surroundings, the total change in energy should be 0. First step of this lab was to analyze the experiment in tracker. So here's my observed motion of the mass on the spring from the video given to us. Some important info: the mass was 0.402 kilograms. The stretch length of the string was 0.07 meters, and the initial position and velocity are both shown on the screen. Last week, we had to solve for some initial conditions, including spring stiffness and relaxed length of the spring. I found that the spring stiffness was 6.83 newtons per meter, and that the relaxed length was 0.123 meters. Now moving on to the computational model. First, we can start with how I computed the spring length and system energy. The length of the spring can be found by subtracting the relaxed length of the spring from the stretch length, as you can see in the first lines of code. And then computing the energy of the system, it was simply typing in the equations for kinetic, gravitational, and spring potential energy, and then adding them all together to get the initial total energy of the system. All right, now for the while loop. So all this is calculating the change in energy between each timestamp in the loop. So I did this by calculating the gravitational force, spring force, and net force using equations discussed earlier in the video. Then using Newton's second law, if we have the net force, we can find both velocity and the position of the mass. Using these quantities, we can find the kinetic and potential energies of our system, and then finally the change in energy between each timestamp. Now we can get to conclusions and comparisons. The picture in the top left is a screenshot from the video of the computational model while it is oscillating, and the red dot there is the experiment. The two graphs on the right show the information graphically, and as you can see, the blue line here is the computational model, and the red line is what I calculated in Tracker. From these graphs, we can see that towards the beginning of the data, the lines were closer, and they slowly deviated apart from each other as time went on. This is because in reality, the system is not isolated, and the surroundings and drag force are shortening these oscillations. Another possible error is that my center of mass points in Tracker that I clicked on were not accurate, which is definitely possible. Honestly, I went through it pretty fast, so my bad if that's the case, and that's the cause of error here. Okay, so now for some post-lab questions. Is the energy satisfied? Or is the energy principle satisfied? As you can see in the graph, it is, since there are no external forces in the computational model. We know that there can be no work done, and that means that the change in energy must be 0. Again, the graphs show this with the different forms of energy adding up to 0. Lastly, we will compare oscillation periods in the x and y directions. To do this, I looked at the graphs of the oscillation in both directions to find the periods. They produced different periods, with the x oscillation taking 5.8 seconds and the y oscillation taking 6.8, which result in the deviations in the graphs and what the spring constant is. And that is all I have. Thank you all for watching.